in elliptical orbits around the Sun. Kepler's first law told us that. We now know that the distance of a planet from the Sun varies in an elliptical orbit. But here's an interesting nugget of fact. Mercury's top speed is 1.5 times faster than its minimum speed. Why does Mercury have such a large variation in its speed? Kepler's second law of planetary motion has the answer. Let's find out. We have already studied Kepler's first law of planetary motion. According to this law, a planet revolves around the Sun along an ellipse with the Sun at one of its foci. We will now study Kepler's second law. Kepler's second law is a consequence of the physical law of conservation of angular momentum. Angular momentum of a planet revolving around the Sun is given by vector L equals to m into vector r cross vector v. Here, m is the mass of the planet and vector r and vector v are the position and velocity vectors of the planet respectively. The cross product implies that vector L is perpendicular to the plane containing vector r and vector v. The Sun does not apply a torque to the planet from its gravitational influence. Hence, the torque, tau, is given by vector tau equals to d vector L upon dt equals to 0. The angular momentum of the planet, vector L, therefore remains constant. Let us say that the time taken by the planet to move from P to Q is delta t. Delta A here is the area swept by the line joining the Sun and the planet. This is equal to the area covered by the points O, P and Q. It can be proven mathematically that delta A upon delta t equals to aerial velocity equals to modulus of vector L upon 2m. Here, both the modulus of vector L and the mass of the planet are constant. So, delta A upon delta t is also constant. This is Kepler's second law of planetary motion. It states the line joining the Sun to the moving planet sweeps out equal areas in equal intervals of time. This law is often referred to as the law of areas. In other words, if we draw an imaginary line from the center of the Sun to the center of the planet, then the line would sweep out equal areas in equal intervals of time. Let the time interval to cover each region be 1 month. On shifting the same image to a graph paper, we observe that the two regions, blue and green, cover an area of about 30 squares. Hence, this line sweeps out equal areas in a span of 1 month. Let us go back to the equation vector L equals to m into vector r cross vector v. As vector L and m are constant, modulus of vector r cross vector v equals to rv sine theta would also be constant. The angle theta is the angle between the radius vector and the velocity vector. At pericenter and apocenter, the angle theta is equal to 90 degrees. So, sine theta equals to 1. As a result, RV is constant. At pericenter, R is less than that at apocenter. So, the speed of the planet near the pericenter increases whereas the speed at the apocenter decreases. This effect can be seen clearly when the orbit of the planet is highly eccentric.